Hey, Linwood Stat students. This is class for Wednesday, um, April 15th, tax day. Well, not this year, it isn't. I haven't even started on my taxes yet. Okay, let's look at the syllabus, see where we are, and where we're going. There's a little bit. This is the syllabus, the original one. There's a few mistakes here, but they're correct on your calendar. Good Friday was last week, obviously. Homework 9.0, I believe, is due tonight, not last week. And Friday 9.1 is due, I believe. And we're on 9.1, so we're a little behind as far as where we're supposed to be. But this will catch us up a little bit because there is no section 9.3, doesn't exist. Don't know where that came from. Then next week we got a quiz 4. I'm going to do that the same way I did quiz 3. That is, at the beginning of the week I'll post the quiz. Then you can, if you can print it out, good, and write your answers on it. Otherwise, just write your answers on a piece of paper. And then we'll take a picture of those with our phone and post them on campus. So I don't believe there is a homework 9.3. Let's double check here. I'm pretty sure. Quizzes. I guess we could look at the calendar. I'm a little behind in attendance quizzes. Now, see, there is no homework 9.3. I don't know what's going on there. Let's go back to the syllabus. Okay, so next week we've got quiz 4 and nothing here. Then we'll be working on chapter 10 by then, our last chapter. But it's a big one. It's a tough one. It's kind of strange. Different than any kind of math course you've had before, I'm sure. And so then the Friday, the final exam here, this is for section 11. Section 12's got a different day here. That we'll still have to talk about. Anyway, we have some time left. Not a lot, but we're going to finish all the material that's going to be on the final exam. That's good. All right, let's get going. Where is my tablet? There it is. Section 9.1. Here we're going to be talking about the sample proportion. We'll also talk about the mean or the average of a sample in a population in this section. Okay, so sample proportion is an easy idea. It's a proportion of a population, 20%, 30%, 0.2, 0.3. Strictly speaking, the proportion's a number between 0 and 1, often converted to percents by people who are discussing it. And so what we want to do is we want to take a sample of this population of small n, as we've been using all along. We want to take a sample of small n and find out how many of these people have the characteristic that we're looking for, or Democrat, Republican, or whatever. So the sample proportion, what do we use for that? That's p hat. Yay. P hat is given by x, the number of people that have that characteristic, divided by n. That's the fraction of people who have whatever it is we're looking for. Okay. If n is sufficiently large, then p hat is approximately normally distributed. Okay, so that's the central limit theorem. The requirements are that n times p hat has to be equal or greater than 15. And n times q hat, which is 1 minus p hat, also has to be greater than 15. And the mean of our p hats is given by p hat. The standard deviation is a formula that we've already had. It's p hat times 1 minus p hat over n. So we don't know, it's actually p times 1 minus p over n, but we don't know p. That's the proportion of the population. So we have to approximate p with p hat. And then calculate the standard deviation that way. Okay, and that's what I did in all of these. The mean is p hat, not p. The mean is actually p, but it's also p hat. And these should be p and q. Instead, I'm using p hat and 1 minus p hat. I guess 1 minus p hat you could call q hat, but we don't need to. Okay, so we're going to use those formulas to make our confidence intervals for a population proportion. And first we're going to decide on a level of confidence, beta. Well, I hope you're all used to this by now. Beta, it's of course a Greek letter. But it's how confident we want to be. And I pointed out that the 3 levels of confidence that are most commonly used by humans is 0.9, 0.95, and 0.99. The higher the value of beta, the larger the interval is, because we want to be more confident that our estimate of the proportion is within that range. Within the range, or the true proportion is within that range of the sample proportion. The higher the value of beta, the larger the interval. We refer to confidence intervals with a confident level of, I'm going to pick a number here, a confident level of 90% as 100 times beta. Common values of beta are 0.9, 0.95, and 0.99, which are the 90, 95, and 99 confidence intervals. By common, of course, what it really means is that's all we'll ever use is one of those 3. Okay, calculate the margin of error. The margin of error is how far from the point estimate, that's the estimate that we get from the sample. We need to go in either direction to obtain the endpoints of our interval. The margin of error is always equal to, here's that z number again. It comes from that little table. It's made to look very mysterious here with this little alpha over 2 and stuff like that. We don't care about that. There's nothing mysterious about it. It's just a number, 1.645, and so on. You've seen the table numerous times. And we can calculate the standard of error. This is also called capital E in these notes, by taking the z number that we get times the standard deviation of p hat, which is the formula that I wrote on the last page. I probably am falling into a trap here by not, I gave a little spiel about the different standard deviations there are. This is the standard deviation of p hat. It's the one we're going to be interested in this section. So that's the one that's what goes here. It's the square root of p hat times 1 minus p hat divided by n. Larger values of beta will result in larger values of this z number. We know that we can see that from our table, and thus will produce wider confidence intervals. I don't know what this star means. The resulting confidence interval is this is p hat, the point estimate, minus the standard error, and from p hat. So p hat is right in the middle of the interval, and the interval stretches from the standard error below it to the standard error above it. And that's the way all confidence intervals are going to behave. That's why we talked about them in 9 point, just the general confidence interval, what it is in section 9.0. My foot is falling asleep. Sorry about that. An interval constructed in this way will have a beta % chance of containing the true population proportion P. So I'm going to get an interval, and the center of that interval is going to be the p hat from my sample. The right end of the interval is going to be p hat plus a certain amount, called epsilon or SE or E. And the left-hand side of that interval is going to be p hat minus that amount. And there's going to be a certain % chance, 90, 95, or 99% chance, that my true population proportion is in that interval. That's what statistics is going to tell us. Okay, this confidence interval can be calculated with a TI-83 or an 84. I'll get back to that. These are the steps for it. They're in the notes so you can refer to them. I'm in the process of making a calculator crib sheet for this class. I'm going to try to summarize the calculator steps throughout the semester. We had tons of them. We're going to have quite a few more between now and the end of the semester. So I'm trying to get a calculator crib sheet, and hopefully it will be rolled out next week in time for you to use it on the quiz and on test 4. So anyway, we will see about that. All right, let's do this one by hand. I'm going to do this problem without the calculator. Then maybe I'll do it with the calculator too and see if we get the same answer. It's going to take a lot of time here, but let's do it. A media analyst is trying to determine the portion of people in St. Louis that watch a particular television show. The analyst chooses a random sample of 100 people from St. Louis, and of the 100 people, 20 people said they did watch the show. Okay, this is actually a pretty reasonable problem, I think. Seems like a practical problem, probably something that's been done. Okay, find the sample proportion, p hat, of people that watch the show. Okay, that's pretty easy. That's 20 people over 100. I don't even need a calculator for that. That's equal to 0.2. Easy enough. Is it normally distributed? Justify your answer. Well, here's what I want to answer. Is 0.2 times 100 greater than 15? Well, I think it is, because 0.2 times 100 is 20. And is 0.2 times, is 1 minus 0.2, or 0.8 times 100, greater than 15? I think it is, because 0.8 times 100 is 80. So, yes, that's how I justify that answer. Find a 95% confidence interval for the true population proportion of people in St. Louis who do watch the show. Okay, let's find the margin of error. That's equal to whatever z is for 95%. Well, I have my little table on one of my other screens here somewhere. Let me see if I can find it. somewhere. I'm having some difficulty finding it. Might have to look back a chapter. Oh yeah, it's not even in this chapter. Okay, where did that occur? Maybe in the formula sheet for test 4. There it is. Okay, 95%. Z is equal to 1.96. I should have known that. And then times the standard deviation, which is the square root of p hat 0.2 times what, q hat, or 1 minus p hat, that's equal to 0.8. And I got to divide by 100. Okay. Get my contraption here. Turn it on. I need to take a square root, so I'm going to choose square root. Then I'm going to take 0.2 times 0.8 and divide that by 100. And close my little parentheses, and I get 0.04. I probably could have done that in my head. Sure could have, because 0.2 times 0.8 is 0.16. Anyway, then I got, oh, I didn't multiply by 1.96, so I got to multiply this by 1.96. And I get 0.0784. All right, so the right-hand side of the confidence interval is going to be 0.2 plus 0.0784. I can do that in my head. That's 0.2784. And the this is the left-hand side, or the right-hand side, excuse me, 0.2784. And the other side, the lower side, is going to be 0.2 minus 0.2784. 0.2 minus 0.0784. And I get 0.1216. Okay, so this is the range at which I'd be 95% confident that the fraction of people who watch the show is somewhere in this interval. I'd be 95% confident. That's what that means. All right, well, let's see how the calculator would do this. It's been a while, but it's in under the stat button. Nope, it's not second, it's just stats. And you go over, you just click the stat button, not the second button, and you go over to tests. And then we're going to start looking for a test. Ah, there it is, A. So if I would have pressed alpha A, wherever A is, if I would have pressed alpha A, I would have got this. This is, what is this saying? This is saying a proportion Z interval. That's what that stands for. Proportion Z interval. I'm working on a proportion problem. I'm using, this is going to be called Z statistics. That's not a universal term, but that's a term we're going to use for it. So when we're doing this procedure, we're using Z statistics. And this is interval, INT. So I press enter. If you have an old calculator, it's going to ask for this same information in the same order. It's going to ask for three things. The first thing I put is the number of people that approve of the show. The second thing I put is the number of people in a sample. That's equal to 100 here. And the third thing I put is my confidence interval, 0.95. And then, so you would put, if you have an older version of this calculator, you would have typed 20, 100, 0.95. And then I'm going to press calculate. And here's p hat, 0.2. Well, I did that by hand. And here's the lower end of the confidence interval, 0.1216. And here's the upper, 0.2784. Yay, same thing I got right here. All right, so what I'm telling you is true. Always like to check myself. There's two kinds of people that might lie to you: preachers and college professors. All right, what's more? No more to that example. Well, here's a similar example that's going to be so much the same, I probably don't even have to read it. 527 people, and I've got 1137 voters. So p hat would be 527 over 1137. Is it normally distributed? Well, I don't know. I need to check and see if 1137 times p hat, which I would have calculated in the first part, is that greater than 15? I bet it is. And I would have also had to check, is 1137 times 1 minus p hat, that I would have got from the first part, is that greater than 15? I bet it is, because this is a chapter about Z statistics, and Z statistics use the normal distribution. Okay, find a 90% confidence interval for the proportion of voters who approve of this candidate. Okay, I'm going to do that, but I'm going to use the calculator this time rather than doing all that number crunching. I'm going to press stats. I'm going to go over to tests, and then I'm going to go up to A, because well, there it is, proportion Z interval. And the number of people who approve of the candidate is 527. Notice that 546 and 64 don't approve of the candidate. The fact that the 64 stated they had no opinion, they're not part of the approved, so it doesn't matter. The only thing that matters is that 527 did approve of them. And the number of people in my sample was 1137. Something's going on. And my I want to be 95% sure. Oh, no, 90% sure. Find a 90% confidence interval. So I'm going to make that 0.9. And then I'm going to press calculate. Boy, that was fast. So now I know that p hat up here, my calculator is telling me, is 0.4635. And the 90% confidence interval is goes from 0.43918 up to 0.48783. 0.48783. So my true proportion of people who like Mr. Jones is somewhere in there with the 90%. I'm 90% confident that it's somewhere in there. Notice that this is so much different than a normal math course. We're never sure of anything. And that's the way life is. Determine the margin of error, epsilon. Well, the center of this interval is 0.4635, I'll bet you. And the margin of error is going to be this upper limit minus 0.4635, because that's how far it is. It's also equal to the 0.4635 minus this lower limit. You can use either one. You'll get the same answer. So I'm going to take 0.48783. Back in the day, we had to do this by hand, of course. 0.4635. So this would be the margin of error, um, which is also equal to 0.4635 minus the lower limit, 0.43918. All right, so I'll just take 0.48783, a lot of numbers here, 48783 minus 0.4635. And you get, oops, I wrote 0.4935. Well, let me just repeat that and change that 9 to a 6. You should never have a negative margin of error. That's a sure sign that there's a boo-boo somewhere. Anyway, I get 0.02433. Oh, that's this question down here. They asking me anything else here? Find a 99% confidence interval for the proportion of voters who approve of the candidate. That's going to be bigger, I'll bet you. If I want to be 99% sure that my true proportion's in this interval, then it's going to have to be a bigger interval. So I'm going to press the stat button, and then I'm going to go up to A, and none of this is changing, right? This is just changing to 0.99%, and easy enough. This interval is bigger, I'll bet. So I get 0.42541 all the way up to 0.50159. You see, this is important because the 99% confidence interval gives them enough to win the election, possibly. To win an election, possibly. Doesn't look too likely. I would not be supporting candidate Jones if I only supported winners. P hat is the same thing for this, right? 0.4635. Yes, P hat's the same. So the margin of error is going to be this upper limit, 0.5019, and minus 0.4635. And this margin of error is going to be bigger. So I take 0.5019 and subtract off 0.4635. Then I get 0.0384. So when you hear margin of error on the news about statistical studies, is the margin of error epsilon or E. It's a shame that they have so many, or SE for standard error. It's a shame they have so many symbols for the same thing. I apologize, but it's not my fault. It's going to be larger or smaller than, is the confidence for 90% is smaller than the 99% confidence interval. Why did this occur? I think I've been discussing that. You want to be more confident, then you need a bigger interval. In a recent survey of 875 randomly selected U.S. adults, 243 said their favorite sport to watch is football, American football. Well, we all know that. No way that fraction of people like soccer is their favorite sport. Anyway, find the sample proportion of adults whose favorite is football. Is it approximately normally distributed? Justify your answer. I bet it is, but I would need to know P hat from part A And my calculator is going to give me p hat. And I would have to take n times p hat times 1 minus p hat, or no, n times 1 minus p hat, and see if that's greater than 15. I bet it is. I'll leave that to the reader, to the watcher. Find 90% confidence interval for the proportion of adults whose favorite sport is football. All right, I'm going to do that. I'm going to go to stat, tests. Now I'm going to press alpha A. There it is. And what do I got? 243 people, 243 out of 875. How confident do I want to be here? 90%, not very confident. Then hit the button, and I'm 90% certain that the proportion of people whose favorite sport is football in America, I'm 90% certain that that fraction is somewhere between 25%, 0.2581, and 30%, 0.30262. And p hat is equal to my estimate is 27.77%, or 0.2777, rounding to 4 decimal places. So my sample told me that the percentage of people who like football the most is 27.77%. But I know with 90% confidence that the true percentage is somewhere between 25.81% and 30.26%. Determine the margin of error. Now, this is just what I've been doing. Let's do this check now. Is p hat is 0.277. So is 0.2777 times n, which was 875, is that bigger than 15? I bet it is. 0.2777 times 875. It's equal to 242. It's way bigger than 15. And what is 1 minus p hat? That's is that times 875 bigger than 15? I bet it is. So I'm going to take parentheses 1 minus 0.2777 and multiply that by 875. 632, you bet it is. So as I predicted, this is normally distributed. Once again, we use z for the variable for the normal distribution. That's why these are called z statistics. All the things I'm going to be doing in this chapter are called z. Yeah, no, there's some different kinds of statistics in 9.2. We'll get to. Okay, otherwise we wouldn't have to call them anything. There'd only be one kind, but there's 2 kinds. All right. Determine the margin of error. Well, this is kind of the same thing over and over again. I take the right-hand side of the interval, 0.30262, and I subtract off the p hat, the number that's in the middle of the interval. I'll let you do that on your calculator. Whoa, find a 99.99%. I told you that this is very uncommon. You want to be really, really, really confident. This is going to be a really wide confidence interval. All right, let's do that. Very uncommon to want to be that confident of anything. So let's go back to stat, alpha A. Oops, nope, I forgot to arrow over to test, and then go to alpha A. And 243, that's what we got. 875, that's what we got. I want this to be 0.9999. Sheesh. 0.9999. Wow, I'd be very confident that the true proportion is somewhere in here. That goes all the way from 0.21881, about 22%, 21881. It's about 22%, all the way up to 33.662%, up to 33.33662. Okay, well, I know almost for sure almost, that the true proportion of people who like football in America is somewhere in between these two numbers. A marketing agent is trying to upsell an advertising banner which is on display during football events. In years prior, the banner cost $75, but the agent is now asking $100. The agent explains that in prior years, only 24% of U.S. adults' favorite sport to watch was football. But recent survey by their company showed that a percentage is now 35%. Should you pay the $100 fee, or do you suspect the agent is misleading you? This guy is lying through his teeth. There's no way that the proportion is 35% because I'm 99.99% sure that the percentage is below 33.662%. This guy is probably lying. Okay, whenever people are trying to sell something to you, you have to be suspicious. Okay, choosing a sample size. Okay, we got a couple of formulas here. We're not going to delve into where they come from. We'll just deal with them. Suppose you want to find a sample size n which would guarantee that there's a probability of 90, 95, or 99% that a randomly selected size will have a sample proportion or mean that is within E units. This is what we've been calling the standard error, epsilon or SE, of the population proportion P or the mean mu. Okay, so here's our formula for smallest sample size. It's very similar to the formulas we had before for smallest sample size. It comes from solving this expression for n. It's a bunch of algebra. For those of you who are good at algebra, you could work it out if you want. This, nothing mysterious about this z. That comes from our table. It depends on the amount of n that you choose. Obviously depends on how confident you want to be. And likewise here we need to know the standard deviation of the population. If we're talking about means, if we're talking about an average of a population. And note, we always round n up to the next largest individual because this should always, this n should be the number of people we're going to choose, and we want it to be an integer. We don't want to choose a fraction of a person. It'd be kind of gruesome. All right, now they just want us to apply these. A researcher wishes to estimate the proportion of households as subscribed to the Wall Street Journal. What sample size should be obtained, or she, if she wishes to estimate P to be within 0.07? This is the standard error, or epsilon. Once again, 3 different symbols for the same thing. This is going to determine what that z number is from our table. I got the table sitting right in front of me now. And she's going to use a previous estimate of 21.3% for p hat. Well, as I said, they go back and forth between percents and proportions, but when we're using a formula, we always have to plug in a number between 0 and 1 for p hat. Okay, so now what is that formula for n? I don't know, it's on the last page, the previous page. It is I lost it. There it is. Okay, remember this. P hat times 1 minus p hat times this thing squared. So it's equal to p hat 0.213 times 1 minus p hat, that's 1 minus 0.213, times, and this is all going to be squared, what was upstairs? The z number. The z number for 90% is 1.645 divided by, what was this divided by? I forgot already. N, no. E, 0.07. And I got to square it. That's a big program. But my calculator will take care of it. Turn it on. Take 0.213. We'll just put it in just like it is here. 0.213. I'll put some parentheses. And then I'll put 1 minus 0.213. Put some parentheses. Then I'll put another set of parentheses, and I'll take 1.645. 1.645 and divide that by 0.07, close my parentheses and put a little squared there with the squared button, and I get 92.57. Well, we don't want 0.57 of a person, so we're going to call this 93. Given the population mean of 50,000 and a standard deviation of 4105, find the smallest sample size will guarantee that at least 80%, that's a rare chance of the mean sample income, mu, being between this and this. Give these, what am I looking for? Okay, so they're not telling me what E is. I need to figure it out. Here's mu. That must be halfway between these two numbers, which it is. So I need to figure out E to plug into my formula. And so I'm going to have to take the right-hand side of the interval, 50,500 minus 50,000, and I get 500. So that's what's going to go into my formula for E. Here's my formula that I'm going to use here. It doesn't have any p hats in it because this is for a mean. I don't have much room to work this. N is going to equal sigma, first z alpha, right? It's going to be z for 0.8. That's 1.282. Divided by E, which is 500. Looking for my formula here. Okay, I got to take z times sigma over E and square that whole thing. So I got to take z times sigma, which is in the problem, 4105, and square that whole thing. All right. Need my calculator for that. I'm going to put parentheses, just like I've got it written. 1.282, that's my 80% Z. And I got to multiply that by 4105. Then I got to divide that by 500 and close my parentheses and hit the little squared button. And I get 111 people. Okay. Additional example. A television sports commentator wants to estimate the population proportion of Americans who follow professional football. What sample size should be obtained if he wants to be within 3 percentage points? 3 percentage points. So this is the standard error. 3 percentage points. 3 percentage points. What does that equal? He wants to be within 3 percentage points. So that's 3%. That goes from 3 percentage points above to 3% within 3 percentage points. I say that means the standard error in this problem is 0.03. I might take that back later, but I'm going to go with it right now. And he's using an estimate for p-hat of 8.86. Well, he would get a number that's equal to 0.86. I remember the formula now since I just used it a minute ago. Times 0.86 times what was there? Oh, Z. What do we? 95%. Z for 95% is 1.96. 1.96 divided by 0.03, and I got to square that. Okay, let's see what we get. 0.86 times 1 minus 0.86, not negative, minus 0.86, parentheses. Then I got to multiply that by 1.96, pretty confident, divided by 0.03, and then square that puppy. And I get 514 people. What if he does not use any prior estimates? Okay. Well, suppose I have no idea what the population proportion is, but I'm going to be choosing my sample size so that I get I'm within 3 percentage points with a 95% confidence. It turns out that the this depends on p-hat. This 1.96 depends on my 95% confidence, and this 3 percentage points is how close I want to be. So the thing that would vary is this p-hat times 1 minus p-hat. It turns out that the biggest value you can get, the biggest n you can get out of this formula, the biggest n occurs when p-hat is equal to 0.5. That's, that seems actually pretty reasonable. That's a mathematical thing you can prove to yourself if you that the biggest number you can get out of here is what occurs when p-hat is 0.5 and q-hat, 1 minus p-hat, is also 0.5. Right, you see, p-hat, if that's big, then 1 minus p-hat is small. And if p-hat is small, then 1 minus p-hat is big. So the biggest that this product can ever occur will be is when p-hat and 1 minus p-hat are the same number. So if you don't have any estimate of what the population proportion is, you can find out how big your sample has to be by using 0.5 times 1 minus 0.5, which is, of course, 0.5, times 1.96 over 0.03 squared. Let's do it. So 0.5 times 0.5 times, I'm going to square this, 1.96 divided by 0.03. Squared. You got to do 1,068 people. That'll guarantee you that your point estimate is within 3% of the, with the 95. You'll be 95% confident if you take this size sample. You'll be 95% confident. Is this another problem here? The 95% confidence interval for a population proportion is found to be this. Find the sample size n used in constructing this confidence interval. Okay, this is another problem, a totally different problem. Another example. Okay, p hat must be right in between these two numbers. So p hat must be 0.302 plus 0.384 divided by 2. So let's find that. Excuse me. 0.343. And then the standard error must be 0.384, the right-hand side of the interval, minus 0.343. And .044. Excuse me. Got a tickle in my throat. I'm going to have to stop for a minute and get a drink of water. So finally, let's find out what n is. N is equal to p hat, which is 0.343, times 1 minus p hat, 1 minus 0.343, times z for 95%. All right, let's dig up 95% z. We should know that by now. It's 1.96 divided by the standard error, which is 0.044. And square that guy. And let's do it. Times 1 minus 0.343 times 1.96. This is going to be a big number, I think. 1.96 divided by 0.044. And square that guy, right? 448. Okay, I think that'll wrap it up for today. Let's see what's next here, I think. Yeah, we're up to 9.2. I'll do a couple of examples from 9.1 at the start of class on Friday. Otherwise, hang in there and keep a good attitude. We'll be done with the semester soon, and see you on the other side.